Today on the Perception in Action podcast, how do instructions about task constraints influence how a performer searches for a movement solution? Is movement variability still beneficial even when you guide a performer towards the optimal solution? So it's time for a call to action. Hi, this is Rob Gray from Arizona State University. I've been on a now over 25-year journey as a researcher, professor, and high-performance consultant to understand how we acquire and adapt our perceptual motor skills. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. Before we get to today's topic, I want to tell you about a couple extra things that might interest you if you're enjoying the podcast. First, my book, How We Learn to Move, A Revolution in the Way We Coach and Practice Sports Skills, is now available in audiobook format. You can find it on Audible or Amazon. Second, if you're interested in working directly with me, I currently have openings in my monthly mentorship program. This includes monthly Zoom meetings, either one-on-one or with your staff, analysis of your practice designs, and a monthly group discussion with coaches and instructors from a range of different sports. To find out more, please go to patreon.com/perceptionaction. Now on to the show. Hi everyone, this is Rob Gray from ASU and the Perception Action podcast, back with another article review. In this episode, I want to look at this really interesting new paper by Carl Newell's research group, again, building on their wonderful work looking at the role of search and variability in finding a movement and a coordination solution. So this was recently published in Journal of Motor Behavior. And thanks, Charlie, I really appreciate sending me a kind of a preprint copy of this. So for those familiar, I've talked about this a lot of times on the podcast before. Newell's fundamental idea is learning movement as a search through perceptual motor space, right? And this the twist that's kind of added in this paper and some of the work is that learning is a constrained search, right? So the idea is that, there's some great quotes. Motor learning is fundamentally about the search for and creation of stable regions within the perceptual motor workspace that support obtaining the task goal. Finding what to do with your hands, right, on a tennis racket, right? The search process itself emerges from the task individual environmental interaction, right, the symmetry we always talk about, influenced by the initial conditions, the performer's inherent intrinsic dynamics. And this is the important point that Newell really emphasizes. Learning is not just about this headlong movement towards the optimal movement solution, right? On the way, we're learning about the task dynamics. We're learning about the task constraints, what can and can't be done in terms of the movement solution. And that's really, really important part of learning. So through the search process, learners become attuned to more differentiated information that specifies the salient properties of the task dynamics, right? So you're learning what you can and can't do, and you're learning how to learn to move. You're finding a solution by understanding the space, right? Not just heading headlong to the one solution, right? Along the way, you're making this important knowledge, right? And different kind of knowledge about the task space, which is going to be critical for adaptation and adjustments and things later on, right? And critically, all what we talk about all the time, movement variability is critical because it provides information about the task dynamics, the boundaries of the solution space, right? It gives you this information, even though when the movement variability might not be directly related to the end goal, right? Or something you want to be doing in the end, right? That all these tasks we use in sports where we give you a different ball weight, or in pitching where I have someone throw on a mound that goes uphill. Obviously, that's not something you're going to do in the actual sport, but it's giving you information about the solution space, right? Which is very useful. Okay, so that's the fundamental idea of learning. Okay. The issue is, though, right, and what they've shown, Rajiv, who's been on the podcast before, and Carl, their great work has shown that there's not just this simple, wonderful relationship between variability and performance and learning, right? Not all variability seems to be good. And oftentimes learners can get stuck in what's called a local minima, right? So they get stuck in a good but not great movement solution, something that just works, right? And this paper here, Search Strategies in Practice. If you go to my YouTube channel, I think it's in 2021 article reviews. I talk about a great study that Carl did related to that. So the idea is that, this understanding the task dynamics in search engine space is useful and important. But of course, as a coach, right, we want to guide it somehow. We don't want to let people just running off on their own. People learn things, but maybe we can make it more efficient. And the important point that they make in this article is that the information I get about task space is not restricted just to what I pick up during the execution and exploration, right? It's also related to the information I give before practice. I'm given before practice, instructions from a coach, demonstrations, right? These serve as a role in guiding or constraining the search that I'm about to do. Okay. Instructions may help to make the search process more efficient by eliminating non-solutions to the task, especially when tasks become more complex. Instructions, therefore, have the potential to guide and constrain the search process in the learning task. This is the fundamental idea of the constraints-led approach for me, right? We're giving you something to help your search. We're giving you something that constrains your path of search, right? Either taking you away from something that won't work or pushing towards something that we think will. Instructions are providing forward-looking information that would guide the learner to the most salient feature of the task constraints. Critically, what we want instructions to do is to give the learner information about the task constraints, not guide them to some ideal solution. We want to give them information so they can find it on their own. But this may involve kind of pushing them to a certain area of task space. So in this study, what they're going to do is use a force coordination task. So a task where you have to push down on force plates with two hands, and there's a certain algorithm that you have to try to match, right? And I'll tell you more about that in a second. They have basically split participants into two groups. One that just did the task, and one that was given feedback. One that was given instructions about the task space. Okay, so their main hypotheses were these three: being provided instructions about coordination would lead to enhanced level of performance. Right. So if I give you some instruction that's going to constrain your search, you should perform better, right? Because you should get to a solution faster and stabilize quicker. Providing instructions about the two hands should be coordinated will restrict the overall area of the task space searched, right? If I'm going to push you to a certain area of task space with an instruction, right, you should show less variability in your search. Why would you go way over here when I've told you the search is over there? Without instructions, the idea is that if we're not given instructions, then greater variability is probably a good thing, right? We don't know where the right answer is, so searching wide and far is probably a good thing. If you're given instructions, doing a wide and far search may not, at the very least, it's probably not going to help a lot, because we know, where the optimal solution is looking all around and trying really weird things. Their hypothesis is that at the very least, that might hurt. At the very least, it's probably not going to help when you're given a specific instruction. Okay. So as I mentioned, their task had 32 participants split equally into two groups. The task was involved, as I said, was a force production task where you're shown your force on the screen in terms of a colored line. Then you're shown the goal force in terms of another colored line. The goal of the task, what you're trying to do is adjust your hands so that the two lines fell on top of each other as much as possible. The actual algorithm was based on the coordination, so the total force didn't matter. So you could produce a correct solution where the two lines were aligned by pushing very lightly or very hard. There was lots of different things. The no instruction group were told the goal of the task was to match the red and yellow lines to achieve the lowest error score as possible. The instruction group were told that, and they were also told that the error between the red and the yellow lines will be reduced by maintaining equal pressure between each hand. Right. So there's this algorithm that generates the goal line. The instruction group were told, okay, here's the area in the solution space that's going to where the solution is. Right. So they're given some guidance about the task dynamics, right? The kind of rule about the task space. Okay, so those are the two groups. They measured a bunch of different things in terms of variability and performance, and I'm just going to go through some of the basic results. So this is the error, right? So you can see as you go through the practice blocks, the instruction group is showing a significant reduction in error. The no instruction group was not. Okay. So clear performance benefit for the instructions. Okay. Interestingly, so that matches their first hypothesis. The second hypothesis, for the most part, was supported as well. This is showing the area of space in terms of different forces in the two hands that was searched for the two groups. You can see the instruction group used very, very small range of solutions, right? Most of them were where the two hands had equal forces, right? So the instructions very, very helped them. The no instruction group did too, right? They used a lot of solutions where they're equal force in two hands because they learned about the task dynamics on their own and they figured it out. But they used a much wider range of those solutions, and they also had a lot of solutions that were off the kind of goal line, right? So kind of what you would expect. Okay. The other thing they did in the study, kind of matching their third hypothesis, was they looked at the relationship between the error, your performance, the amount of variability, and the instructions, right? And then the basic hypothesis they had, right, was that if I give you instructions, then the amount of variability you show in terms of searching the space shouldn't really matter, and it might actually hurt. Whereas if I don't give you instructions, more variability will be better. Kind of consistent with all the work that they've done in this area. The story was not that simple at all, right? What they found was actually large individual differences within the groups based on how the solution changed over practice, right? Some people started with a low force solution and increased. Some did the reverse. And that seemed to shape the role of variability. A key point, I'll go over this again, is that some people in the instruction group, even when they were told, here's the optimal solution, equal force in two hands, here's the task dynamics, they still benefited from having greater variability in the search space, right? Whereas others did not. And the same was true in the no instruction group, right? So it was not a simple relationship. So what are the conclusions from this study? That variability in task space to pick up relevant information depends on the instructions given, right? Overall, right, when you're given an instruction about task dynamics that kind of guides you to a solution, you search this task space less. Okay, and it influences the solution. The instructions influence the emergence of your solution in a complex way, right? Not in a simple, direct way where you immediately go to the solution. But right, we should recognize that you get the same information from searching the task space yourself without the instructions. It just might be more efficient to give you instructions. Okay. There's this complex emergent relationship between instructions, variability, and search, right? It's not a simple the case that when I give you instruction, you reduce the search space and you find a solution, right? Some people are still going to benefit from variability. And this is the last point. Movement variability seems to be a necessary part of learning, even when participants are given instructions that direct them to an optimal solution, right? And I think this is something a lot of us would agree with, right? Even if we, learning, because you're learning about the task space, the task dynamics, not only is that going to be helpful in finding an initial solution, but when you need to adapt to changes in constraints and things like that, I think it's going to be very useful. And this is something, I found in some of my batting studies that as well, this benefit of movement variability. So as I said, this is another, I think, this one, for example, I found this kind of interaction between instructions and variability as well. And this my batting study, comparing the constraints-led approach and differential learning. So overall, I think, again, this adds to this really wonderful body of work that Newell and colleagues are doing on search and variability in the task space. So I think it's a really interesting article. Okay, that's it for today. Thanks for joining me. You can find everything you want to know about me at perceptionaction.com. This is Rob Gray from ASU. Cheers for now, and keep them coupled. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or follow me on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including written transcripts, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep them coupled.
Gone straight away.